Now we want to look at the relationship between voltage and electric field. In order to do this, we need to understand the idea behind a uniform electric field. As we saw before, one of the easiest ways to do this is to compare it to a gravitational field. We can look at two analogous situations. One is a ball M rolling down a hill. The other is a charge Q moving through an electric field. First, let's look at the gravitational field. We could say that at any point along the Earth, there is gravity acting on an object. We could even go so far as to say that the gravitational field is uniform in that an object acting at any given distance away from the center of the Earth has the same force acting on it. A uniform electric field can be created as well. If you have a sheet of positively charged metal in proximity to a negatively charged sheet of metal, the electric field points from the positive sheet to the negative sheet uniformly in between. In a gravitational field, the force felt on an object is determined by its mass and g. In an electric field, the force is determined by the magnitude of the charge and the strength of the electric field. Now, if we move the ball in such a way that it moves against the gravitational field, then that changes the energy of the ball. So increasing the height changes the energy because we are moving further away from the source of the gravitational field. The same can be said for the charge moving through a uniform electric field. In this case, we are talking about moving the charge from point A to point B, moving with the field. But we could just as easily move from point B to point A and get the same change in energy. So moving some distance against an electric field changes the energy of the charge. If you have a certain mass at a certain height in your gravitational field, you can determine how much energy you have. The idea of potential is that that specific mass has a certain amount of potential within the field. So we don't really need to worry about the mass involved because it stays constant throughout. So the potential of the object really only depends on the field and the height above that field. The same thing can be said about the potential in an electric field. The potential really depends on the change in distance within the field and not so much the magnitude of the charge. If we then differentiate the potential with respect to the linear change in height, we find that the field is simply equal to g. Likewise, differentiating out the electrical potential with respect to distance, the field turns out to be E. We want to look at this relationship between electric potential and electric field a little bit more closely. Potential is more closely tied to the energy of the particle and is actually a scalar quantity. Field is more closely tied to the force on the particle and is a vector quantity. But they can be related to each other by calculating the work done by some force moving a charge from A to B. We know that the change in potential energy is equal to the change in work. If the change in potential energy is positive, then the work done is negative. If the change in potential energy is negative, then the work done is positive. We also know that the work done by a given object is the force applied over some distance. This translates in electrical terms if we take into account the force applied by the electric field, which is QE. So in terms of an electric field, work done by a charged particle is the magnitude of the charge times the strength of the electric field times the distance that it moves. This is electric potential energy. Now the potential difference between these 2 points is simply delta V. As with any delta, we can find this difference by taking the final potential and subtracting the initial potential. In this case, we're actually going to take the negative delta V, so we can rearrange our expression to say that the change in electric potential is the potential at point A minus the potential at point B. This just cleans it up a bit, and we can just give the change in potential the designation of V sub AB. This is good because remember that electric potential is actually the strength of the electric field over a given distance. So our work equation can also be written to reflect the change in potential. Now we have work done by a charge equal to the negative potential energy of the charge equal to the magnitude of the charge times the strength of the electric field times the distance. And this is all equal to the magnitude of the charge times the change in potential along its path. But wait, it gets better because we can take those two expressions for work and set them equal to each other. We can cancel out the charges to find a lovely expression for the voltage across 2 points in a uniform electric field. So the change in potential of an electric field is equal to the strength of the electric field times the distance that charge moves. So what is the maximum voltage between two parallel conducting plates separated by 2.5 centimeters of dry air if air will support a maximum electric field strength of 3 times 10 to the 6th volts per meter? Pretty straightforward in that we know the electric field and we know the distance. So finding the voltage is just a matter of plugging those into the equation. Of course, we're going to double check our units to make sure they all match up. And we find 7.5 times 10 to the 4th volts. Now suppose an electron gun has a parallel plate separating by 4 centimeters and gives electrons 25 kiloelectron volts of energy. What is the electric field strength between the plates? We are given the distance and the voltage, so it is a pretty simple matter again to find the electric field strength. Remember that 1 electron volt is the amount of energy that will accelerate an electron through a potential difference of 1 volt. So if we have 25 kiloelectron volts, then the potential difference must be 25 kilovolts, or 25,000 volts. Divide this by 0.04 meters, and you get 6.25 times 10 to the 5th volts per meter. So then, what force would this field exert on a piece of plastic with 0.5 microcoulomb charge that gets between the plates? Well, we decided that the force of an electric field is the charge times the strength of the electric field, so that seems pretty simple. Remember that micro means 1 millionth, or 10 to the negative 6th, and we have a force of 0.313 volt coulombs per meter being exerted on our plastic. If you're looking at that label and wondering what in the world that means, remember that 1 volt per meter is equal to 1 newton per coulomb. And if we move those labels around, we get an expression for 1 newton, and therefore we can write our answer as 0.313 newtons as our force. Now, an electric field, whether it is uniform or not, will point in the direction of decreasing potential. The force on a positive charge is always in the direction of the electric field, and in the direction of the lower potential. So if Q is positive, it will be pushed away from the positively charged plate on the left because like charges repel. The force on a negative charge is always opposite the direction of the electric field and in the direction of the higher potential. This is because opposite charges attract, and the negative charge will be pulled towards the positively charged plate. Something else to consider is that the magnitude of the electric field corresponds to the rate of decrease of the potential over some distance. So positive charges seek a low potential, and negative charges seek a high potential. The work done on a charge is the magnitude of the charge times the electric field times the distance the charge moves. Another way we can annotate this is to write D as delta S. This is reasonable because QE is the force, and delta S is the distance, and force times distance is work. And electric potential is found by dividing the work by the charge, so we can substitute that expression in. So now we have a nice general relationship between the electric field and voltage, where E is the strength of the electric field, V is the voltage, and delta S is the distance over which the change in potential occurs. The negative sign just tells us that the electric field points in the direction that the potential decreases. So as we move away from the beginning of the electric field, the potential decreases. Electric field then is said to be the gradient or slope of the electric potential.